pictures. You didn't know.
You go, point to it.
Right. So our next speaker is Mark Swain from JPL. And he's going to talk about the future again, this time the future of planetary atmospheres, JWST, Ariel, HWO, and ground-based telescopes. All right, take it away, Mark.
Well, thank you. I really don't know what the organizers of this meeting were thinking about when they assigned this topic to me. 3 major space observatories and all the ground-based telescopes and a period of about 25 years. That's rightfully the topic of about a week-long workshop. So the way I'm going to address it is I'm going to, since this is a workshop, I'm going to go through a little comparison exercise to compare a couple of these observatories to highlight synergies. And then I'm going to pick some highlights of work that's relatively current over the last year or 2 or 3, which I think foreshadows some of the highlights of this 25-year journey. For me, the journey is really characterized by focusing on the big questions, which are how do planets form and evolve? And ultimately, are there other habitable worlds around other stars where life exists? This is an amazing journey. Honestly, it's a privilege to be a very small piece of it. And to help tell the story and its very compelling nature, I'm highlighting some art from the La Cañada High School art project, which again will help give voice to some of these themes. All right, so let's start by comparing James Webb and Ariel, which are 2 very different observatories and take very different approaches, but as I hope you'll see, are extremely complementary in how they help us understand exoplanets as a class of objects. There's just 2 ideas that I want you to keep in mind as we do this comparison, and that is that for relatively bright objects, there may be a few weird corner cases that people can think of, but for relatively bright objects, the signal to all things being equal, so if I keep the spectral resolution equal, SNR, the signal to noise in each spectral channel, is proportional to telescope diameter. If I hold the spectral resolution, if I hold the signal to noise per spectral channel equal and adjust the spectral resolution, that scales with telescope area. And this is indicating something for us that smaller telescopes can still make a very important contribution, and that kind of the unique discovery space of big telescopes, where they really stand out, is in leveraging spectral resolution. All right, so I think everybody knows about James Webb. This is, the most amazing observatory humankind has ever built. It's got wavelength coverage from the visible to 28 microns. It's got 4 instruments with lots of different modes. This is an amazing facility for exoplanet work. I hear people pointed at other things. I'm not really sure why, but unfortunately, we do have to share it with them. Ariel takes a different approach. This is a meter class telescope. It has 1 instrument mode. It has broad instantaneous spectral coverage from the visible to 7.8 microns. So the one-shot spectrum is very nice because you don't have to stitch together spectral coverage across different transits. As we'll see, this 1 instrument mode is going to be an important benefit, and this is an observatory that's dedicated to studying exoplanet atmospheres. If I lean a little bit in this talk into Ariel, please forgive me. I'm leading the US contribution to the Ariel mission, and I'm really excited about this, and I think it's going to be just a great benefit for the whole community. So when we compare Ariel and James Webb, what we see is that James Webb is really optimal for detailed investigations of specific targets. It offers PIs the opportunity to tailor their observations to specific questions with the variety of instrument modes, and that's a really useful thing. Also, its very large size and its attendant large spectral resolution are great for investigating small planets, and I think this is an area where James Webb is going to do amazing stuff. Thank you. Apologies to those of you online. Ariel, by contrast, is wonderful for surveys, right? Every single observation is made exactly the same way. This means that when we find differences between the observations of different planets or planet systems, we can interpret those as due to astrophysics instead of due to changes in the instrument transfer function between different instruments, for example. So Ariel really excels for statistical comparative planetology. All right, so I'm going to spend the rest of the time picking out kind of 4 themes. We'll talk a little bit about small planets with James Webb. We'll talk a little bit about population studies with Ariel. We'll talk a little bit about habitable worlds with Habitable World Observatory, and then look at some high spectral resolution observations with a ground-based telescope. All right, so my first highlight, again, these are recent work, which I think foreshadows things that will happen over the coming years that we'll see a lot more of. This is a beautiful observation of TOI 270D. This is a sub-Neptune, 4.7 Earth mass, 2.1 Earth radii, 380 Kelvin equilibrium temperature. The spectrum, visible to 5 microns, shows lots of molecular features. And the authors do a really beautiful job of going through the analysis of what's in the atmosphere. The thing that I think is most interesting about it, though, isn't all the molecules they find. It's this business of interpreting the high metallicity atmosphere in terms of a miscible envelope for a sub-Neptune. And their idea there is that the envelope is dissolving material from the core, and this gets mixed. And that's what we're seeing in the envelope is essentially due to this miscibility of core material. So they are using the composition of the atmosphere to make an inference about interior structure. And I think that's super cool. Now, there are other reasons why metallicity can be enhanced, and I'm sure that this whole area will be the topic of subsequent observations. But I really wanted to point this out because it goes beyond just the what's in my atmosphere to what is the interior of my planet like. And that's a pretty exciting thing. Second observation I want to highlight is of this super Earth. Actually, it's not a super Earth. It's a smaller than Earth. It's a terrestrial planet, radius 0.85, 0.4 Earth masses. This is L9859D. Oh, B, sorry. And this is another JWST transit spectrum. This is really interesting. Because of the size and the relatively warm 630 Kelvin equilibrium temperature of this planet, and again, it's small size, at this point, there really shouldn't be any primordial atmosphere. So the authors argue that this planet lost its primordial atmosphere, and yet they detect a transit signature, and both the presence of that atmosphere and its composition lead the authors to infer that this is due to volcanism. So this is pretty interesting stuff. Here we have a terrestrial planet, secondary atmosphere, due to the composition, again, revealing something about the mantle composition. So I think we're going to see more work like this with James Webb also. So again, another very exciting small planet observation connecting atmospheres to some part of the interior. Let's move on to Ariel and take a look at some population studies. This is some work we've been doing inside the Case Science team. And what we've been doing is looking at how well we can constrain the carbon to oxygen ratio in a tier 2 Ariel survey. So in the Ariel language, the tier 2 means a certain type of quality on the spectrum. To give you an idea of what that looks like, here is a Ariel tier 2 spectrum of HIP 65AB. These are all simulated spectra. You can see that but they are of real known planetary systems. So in this synthetic survey, which is representative of what Ariel might be able to do, but certainly, there's no decision about what the survey will be at this point. We constructed a synthetic survey And we find that the ability to constrain the carbon to oxygen ratio is really good, typically about 0.1 dex. So constraining the carbon to oxygen ratio is important because it is believed that the protoplanetary disks have a compositional structure and that the carbon to oxygen ratio of the planet will reflect the environment in which it formed. And so potentially by measuring the carbon to oxygen ratio in a large survey, we may be able to find what fraction of the planet's formed where in the disk. Another area where Ariel is going to be able to make a very substantial contribution is in the measurement and characterization of what's called the mass metallicity relationship. So this has been known about and studied for some time. The mass metallicity relationship is a trend that is believed to exist between the mass of a planet and the metallicity of the envelope. I'd be happy to talk to anybody offline about why that would be. The really interesting thing, though, is that you can measure this more than one way. And so what Ariel will be able to do is do a very large population survey of measuring the mass metallicity of envelopes, which probe the outer layers. But you can also measure it you can also probe the metallicity using the bulk density. And if you compare a bulk density derived mass metallicity relationship with a transit derived mass metallicity relationship, you can make an inference about the interior structure. You can look for composition gradients, which are very important for modulating heat flow. They can suppress convection in extreme cases. It can modulate the magnetic field formation. This is all well studied in our own solar system, and we may be able to start looking into the interiors of planets with Ariel, and I expect this will be a very exciting area of investigation. Another place Ariel can make a really nice contribution is in phase curves. So as transiting planets orbit their stars, if one observes throughout the entire orbit, and if the planet's sufficiently hot, you can measure a system phase curve. So this was done extensively with Spitzer. Spitzer devoted over 4 months to these kinds of observations. Unfortunately, that was done in the Spitzer warm mission, and you had to pick whether you wanted a 4.5 micron light curve or a 3.5 micron light curve. Ideally, you'd want both. Ariel, of course, will have a spectrum, which will be really amazing. Here I'm highlighting some work in a recent survey by Lisa Dang showing a whole catalog of 4.5 micron phase curves. But Ariel is definitely going to take this to the next level with the spectroscopic phase curves, and something like 4 to 6 months of Ariel time invested in a phase curve survey would deliver a really transformational data set that would be a long-term legacy of the mission. Now, one of the challenges in catalog type of analysis is that we need to understand how the conclusions we reach are sensitive to the priors that we bring to the process and the details of the data analysis. Here is some work by a graduate student who's been working with Lisa Dang and my group, Emmeline de Kock, who's been comparing the phase curve catalog results. And the good news is the overall trends match pretty well. The other news is that some parameters, such as, if I can get this pointer to work, such as the phase curve offset, have quite a bit of scatter. And so that identifies an area of further study to try to understand how the analysis is impacting the results. But for all statistical studies, this is a direction we're going to need to do more work in, which is comparing and to really understand how our assumptions are connected to our inferences. Now I'd like to turn to Habitable Worlds Observatory. This is a beautiful simulation of an observation of Earth 2.0 type thing by Mario Danmo and Renyu Hu that was published a couple of years ago. It shows what would be a landmark spectrum. So this is the sort of thing we hope and dream for. But it also shows the importance of broad wavelength coverage. And Vanessa mentioned this some. And I think this is these types of theoretical studies to to really fine tune the instrument design, the trade between wavelength coverage, signal to noise, spectral resolution. These are things that where more studies of this kind are needed. But oops, when HabWorld's Observatory arrives on the scene in hopefully 15 years, but maybe more like 20, this will be this will be one of what's hopefully a number of Earth 2.0 spectra, and we can start looking at the differences between Earth-like worlds, which would be an amazing result. Finally, I want to talk a little bit about, oh my gosh, I have tons of time. I didn't realize this. I have to tell you, every time I've practiced this talk, which is 5 times now, I have been at like 35 minutes. So I've been terrified the whole time. Well, I have gobs of time. You can take a nap now. I don't know what the story is, but I'm going to have you out of here early. That's good, right? Coffee sooner. But before we get to the coffee, we got to talk a little bit about high resolution observations. So these are some super high resolution R of 100,000, so very high spectral resolution. Measurements of a hot Jupiter. This is WST 76b. If memory serves, this is like a 2200 Kelvin equilibrium temperature, but I don't have it written down. It's pretty hot. And I want you to look at the number of species that they detect in that atmosphere. And the ones on the end, the sodium, the lithium, the potassium, and what is that, titanium and aluminum, and I'm not even sure what SC is. On the other, there's some stories about those, but the ones in the center here are very special. So there's 7 elements. And for these elements, they find that the elemental to iron ratio follows that of the C1 carbonaceous chondrites in our own solar system. Now, these are the most primitive of the carbonaceous chondrites. They're believed to form way out beyond the snow line, 4+ AU. They have their composition reflects, most closely reflects the protosolar nebula. And so we have a planet that's in a 1.8-day orbit which has evidence, okay, maybe not decisive, but pretty exciting evidence that the composition of the bulk atomic composition of this atmosphere comes from much further out in the original protostellar disk around WST 76. Now, this is connected to the whole question of how do hot Jupiters form, and there are a number of ideas about that, ranging from in situ to various types of migration. This obviously would suggest a migration type of scenario. But the ability to do ratios between the abundances of specific elements in planetary atmospheres is a really powerful diagnostic. I am certain that more of this is going to be done over the next 20 years, and it's going to be pretty exciting. I further suspect that when we get ELTs doing this, we're going to be looking at isotopic ratios, and that'll be really exciting stuff also. In our own solar system, of course, the isotopic ratios change as a function, with different planets. And that's believed to be due to a variety of factors, ranging from differentiation of the isotopes in the protoplanetary disk to evolutionary mechanisms like the way in which Venus lost its water. So really exciting stuff to be able to do detailed atomic abundance ratios. And again, I'm sure we'll be seeing more of that in the future. So to summarize, we have, we have detailed atomic abundances, which I didn't really cover it, but you can also probe the winds in the upper atmosphere with these high resolution measurements and the Doppler shift in the lines. We have, and we have the ELTs coming. So this will be a growing and interesting field over the next 20 years. We have what I'm certain will be many measurements that will characterize small planets and terrestrial planets with James Webb. We're going to do statistical characterization of various subclasses of exoplanets with Ariel. And with HAB World Observatory, we'll ultimately be getting the reflection spectra of temperate terrestrial planets around solar type stars. Hopefully some of those will look habitable. This is an amazing lineup. Like I said, I'm humbled by it, and I'm really pleased to be a tiny part of it. But this really isn't my story. This is your story. And so my charge to especially the younger generation at this workshop is, there's a brilliant science future out there. You're going to invent it. I look forward to reading your papers. Thank you very much.
All right. Thank you very much, Mark. Great talk. So once again, if you have any questions, come on down to the microphone. I will use my power as chair to say if you ask Mark a question, you will also get a Roman chronograph sticker there. All right. First question.
I can yell out the Zoom people. Thanks. Oh, cool. So 2 questions. You mentioned that Ariel is going to go reach out into the visible or optical a little bit. Is there any chance to study sort of cloud and haze properties? Do you have enough wavelength coverage to do that kind of work to see those slopes in the optical? And then second, I'd love to hear more about this art project you did with high school students. Yeah.
Okay, so question 1 first. For the cloud and haze properties, yes, we will do that with Ariel. In fact, measurement of cloud and haze properties is a case level 1 science requirement. So we do expect to do a lot of that on a routine and statistical survey type basis. And I'd be happy to talk to anybody in the coffee afterwards for more details on that. The La Cañada art project was something I did, and I really have to give all the credit to the students. What I did is I made a personal donation to their program, and the terms of the deal were that everybody who was intermediate through senior student in that program had to do a piece of original visual art on the theme of exoplanets. And in fact, I didn't do this as an assignment. I really asked for their help. And so my request was that exoplanets is an amazing story, and there are 3 major thematic elements. There's the journey. This is the journey humankind has been on, since ancient times, literally, to understand our place in the cosmos. Then there's the discovery theme. We're finding all sorts of exoplanets, and there's a crazy variety of these things, right? From lava worlds to ice worlds to things with a density of styrofoam. It's just, things with a very high density. So there's this huge variety of these worlds, and that's connected again to the discovery theme. What are we finding? And finally, there's the theme of the personal theme of the scientists who make this happen. So I charged them to give voice to these 3 themes and to help tell the story. And you're seeing some of the highlights of their art. We did an exhibit outside one of the buildings at JPL, and we did that in conjunction with the Exoplanet Exploration Program. It's been a real success, and generated a lot of good stuff to put in my talks too.
All right. So while you're thinking of other questions, I do have one. You were given the small task in your talk to talk about 3 present and future space telescopes and spectroscopy from those, and current ground-based telescopes. What about ELTs? What about future trans-spectroscopy prospects from larger telescopes?
So, I think the high spectral resolution, this goes back to that whole thing. How does, if you hold everything constant, what scales with aperture diameter, what scales with area? So the big win for the ELTs is spectral resolution. And I think putting ELTs with R of 100,000 spectrographs or maybe R of 200,000 spectrographs on exoplanets is a great idea. And maybe in extreme cases, you can push down to terrestrial planets. I mean, there have been studies about that. It's hard even for an ELT, but it's under favorable conditions. In some cases, it may be possible. But instead of just focusing on the smallest planets, you do an R of 100,000 spectroscopic uniform survey on a sample of hot Jupiters, and it'll be transformational. There's the potential to resolve the question about the formation. There's a potential to look at all sorts of very complicated dynamics about transport between the day side and the night side, what species condense and when they don't. In some of these observations, they see stuff which in the condensate or signs of the condensate form coming over the terminator in one direction and not in the other. There's a lot of really cool stuff with high spectral resolution. So I think ELTs will play a very important role there.
All right, awesome. And if you think of more questions, go ahead and put those in the Slack. So make sure to tag the speaker you want to ask the question to.